Here we are, round two, if you want to call it that, with Dr.
Sure.
John. And today I have Nathan Thompson with me. And Dr. John, we had a very interesting podcast with your buddy who didn't like anything I had to say, but you seemed interested and you want to learn more. And hopefully you came back with some deeper questions, but we can go anywhere you want to go in this discussion. And let's start.
Yeah, sure. So I suppose the thing that I appreciate about what you and people in Flat Earth are doing is that you're raising some healthy degree of skepticism about some science that is mostly regurgitated in books and through school, etc. And I do agree that most people do not understand or fully know what they quote unquote know. So
What they
that's
believe.
where, well, they're taught something and then they have to take a test and then they have to,
Right.
pass the test. And they don't and school moves in a pretty quick rate. You get thrown everything in every which way. So yes, I mean there's plenty of things that I remember learning as in elementary school, like Columbus discovered the world is round, which that's not even a true account at all. So, you know, it's not impossible to fathom that you do learn some misinformation, and you don't. There's not a critical thinking element in most of school.
We're on the same page. In school they teach you this is what you have to learn. You memorize it, you regurgitate it, and you get an A. And if you get enough of those A's, you can become the next teacher for the next generation. So you're not allowed to challenge anything. I think we discussed that a little bit on our last episode, where if you go against mainstream science, it doesn't go very well for you, especially if you're like funded with grants or anything like that.
Yeah, well, there is a pressure to yeah at the higher level. Yes, there is a pressure to to further the theory and things like this.
Yep.
I okay, so but this is where we might start to deviate a little bit here. So I it's really important to test and to figure these things out for yourself. I think without pictures or without any sort of satellite imagery or any sort of video, I think most people would be very hard pressed to and I've asked people too, like how do you know that the world is a globe? And it's it it's a hard it's challenging. I mean, the original civilizations thousands of years ago all had flat Earth models, and that was the going norm thousands of years ago. Maybe we might have different ideas of ancient civilizations, but some of the archaeological records show flat Earth, was the first mode of thought in human civilization,
They were
and it
teaching
was
flat Earth in American schools up to the 1950s.
well. I think I did catch a video of one of that you had with somebody that had said something like that. I I can't account for all schools, but I'm sure there were some that were teaching flat Earth, but not all of them.
No,
And again,
well, I don't
you
know
said
that.
well, but you also said that schools aren't necessarily
Well,
the be all end all for facts either, right?
well, correct. The Rockefellers took over the school system in 1901 or '02 or somewhere around there, and that's when everything kind of went away from learning into indoctrination.
Well, I don't know that, but perhaps there is definitely standardization in curricula. There's standardized testing, so there's like definitely some sort of group of facts that people are expected to learn in school, for instance. So, but again, the sphere model was a radical way of thinking 2,000 years ago, but that's when it started developing, was with the ancient Greeks and the um, yeah.
I have a slight objection to that. Like, how do you know, other than the people that rule our society told us that the ancient Greeks thought the Earth was a globe back then? Nathan, you can jump in
Well,
anytime you want to throw in a comment.
I mean, there's Aristotle's physics, if you believe that that was a real thing. But I mean, you have to, I guess you do have to pick and choose what you believe and what you don't. But and yes, I wasn't around 2,000 years ago, but that's where the geocentrism came from, was Aristotle. I mean, in his physics book. Now, but don't get me wrong, there was a lot wrong in that book. I mean, this is like the kernels of these thoughts. So, I mean, Aristotle said that heavier objects fall faster than lighter objects. That doesn't turn out to be the case either. There was speculation. There was no smoking gun on a spherical model back then, but the ideas of a spherical Earth had started emerging, 200 BC, 300 BC.
They provided you a historicity of the globe, but that doesn't make it true, right? They could have just invented these characters and claimed, oh, they put some sticks in the ground, which Neil deGrasse Tyson admits works on both models. Eratosthenes was assuming parallel sun rays and the curvature of the Earth, which is what is in.
That was in a and I had some slides on that too. But I mean, I don't, for the viewers, but I don't know how everybody knows about Eratosthenes.
The literature from the 1800s shows that these people all knew it was flat, and they were all going, I don't know what's going on with the people at the top. For some reason, they think it's a globe, but we all know it's flat. And so it wasn't like everyone was convinced of a globe, even just a few hundred years ago. And I just want to say, I agree with you on a lot of things. People aren't taught to think critically in school. Regurgitation is no match for observation. And we're not really taught memory. We're taught cramery. They want you to memorize everything for the test and then forget it over the weekend so they can dump some more information next week. You can cram for the test. And it's actually like a way to program people with neuro-linguistic programming and whatnot. I mean, it's called pacing and leading. Look into that. It's like, oh, well, if I pick something up and I drop it, that must be gravity. And when you're 8 years old, you'll believe it. But the thing is what was the cause of that? You picked something up and you dropped something. So you don't need to invoke magical forces to figure out what's going on there. But if you get someone when there's 8 years old, you can add all this convoluted forces and mechanisms that really you don't need in reality. They're not necessary.
Well, so depending on what they're learning, I think there's probably some superfluous or some things. Gravity is definitely a unique force, though. I mean, yeah, it shouldn't be. To be honest, this is something that I really have a big hang up with flat Earth.
Let's go there for a little. Let's talk about gravity for a little bit then.
Okay, that would be a maybe a good segue here. So, I mean, what is your view on just forces? I mean, let's just forget about gravity. I mean, just the idea of a force.
Well, I don't think it's a force for 110 years. It was superseded by Einstein. Now they call it an emerging property from the bending and warping of space-time. So it used to be a force. Newton thought it was a force. Einstein saw it very differently. According to Brian Cox, he called that force spooky action at a distance. He tried to get rid of it with the bending and warping of space-time, which is pure theoretical, never been experimented on, never been observed in the lab frame, can't be manipulated. It's hocus pocus, booga booga nonsense, in my opinion. John?
Sure. Well, Einstein relativity, there have been experiments that do support the relativity theory, but regardless, I was actually just asking about forces in general. Like, forget about the naming of gravity, or I mean, just like when you apply, if you're lifting a pen versus a textbook, you have to apply more or less force on the pen or on a book.
Right, you're applying a force to lift it up because it's more dense than the medium around it. But you talk about forces. We can talk about electrostatics, which are measurable, testable. We can manipulate them, and we can make things go up and down.
That's right.
Now, can you do that with gravity? Your argument there is, well, gravity, you need a whole Earth to show gravity, right? Like Mount Everest won't make a plumb bob lean sideways because I guess it's not big enough. So we can manipulate the electrostatic force and
but it's a different force.
Well, it's a force, and mainstream science says that the electrostatic force is 10 to the 36 power stronger than gravity. Do you even understand? I mean, you should understand what that means is that gravity is 0. 10 to the 36 is
But
unimaginable. You can't fathom what that is.
yeah, no, it's very small, and that's why electrostatics is significant.
So, but here's the thing:
it's a significant force.
if I can make something go up using electrostatics, right? So, did I just?
But not everything, right?
Well, I can make this go up. I can make this go up.
Right,
when lightning strikes, sometimes people go flying in the air because the electrostatic charge of the Earth changes for a split second, right? So that is evidence saying that there's an electrostatic attraction, right? This is flying because of electrostatics, right? MIT with their silent drone, this has no moving parts. It is flying because of electrostatics. So let's pretend gravity's real. Well, we know electrostatics is real. It's 10 to the 36 power. So when I drop that pen, if I drop this, it goes down. Well, electrostatics is 10 to the 36 power stronger than gravity. If they were both,
are there electrostatics acting on that?
Electrostatics on every single thing, everywhere, all the time. Everything is electrostatic.
But okay, what? I mean, you say electrostatics, and yes, everything has like electrons and protons, and there's charges.
Mm-hmm.
But when you have a charge neutral object and a charge neutral object, equal number of protons and neutrons, or protons and electrons, equal numbers. I mean, the only way electrostatics becomes significant is if there's a charge accumulation on the object. I mean, that's why are you not floating right now? Right?
Because I'm more dense than the ground, than the air around me.
But density, that involves mass.
Well,
right?
Sure, but there is a measurable, testable, provable electrostatic flow from the sky to the Earth. That just sets the down direction, and then buoyancy and density sort everything else out.
Okay, but denser objects, such as, let's say, a lead ball versus a plastic ball, you both drop them at the same time. They're going to hit the ground at the same time. They both have the same acceleration.
Yeah, but doesn't one
that,
John? So the one with more mass should fall faster according to the gravity formula.
No, it does. Okay. So this is a key point, and this is why gravity is a weird force. Just hear me out here, okay? And this is the point I was trying to make.
By the way, there's two of us, one of you. Anytime you want to talk, you talk, and we'll be quiet.
Well, I appreciate it. Yeah, and just try to hear me out here, because I don't, Justin on the previous one, he has like quick zingers and stuff, and I sometimes have to think my thoughts through. But okay, my point is about this: you have to apply some more energy to move this pen rather than a textbook, right? And so you have to apply a larger force if you're moving this versus a pen. But it's very surprising that one weighs more, but when you drop them, they both fall at the same time. The only reason that happens is that this invisible force that you guys like to say is gravity, it has to be proportional to the mass of the object. In order to get the same acceleration for unlike objects, the only way, I mean, how does it exactly know to tune a larger force than on a pen rather than a book? But the only way it happens is if it's proportional to the mass of the object. And that's the insight Newton had. And it's a very profound observation. For 2,000 years, Aristotle said heavier objects fall faster than slower objects. The magnitude of the force acting on the book is larger. The gravitational force is a larger force acting on the book than the pen. But then movement is equal to mass times acceleration. So if you have a force that's proportional to mass, which is equal to mass times acceleration, the mass terms cancel, so you get a constant acceleration. That's why all objects will fall exactly at the same acceleration. That's why gravity is a unique force, and electrostatics has a different operating mechanism.
You said there was an experiment to support special relativity?
So, well, for special relativity, the special relativity was Einstein's first theory, right? And that didn't actually have anything to do with gravity. But I'm sorry, let me go. So, special relativity that was where Einstein made the assertion that light is the fastest moving object in the universe, and that time is relative, and it seemed to contradict the theory of gravity, and that if you move an object, if you move the sun, you know, a light year away, everything will just change instantaneously, and that would be moving faster. That would be like a change faster than the speed of light. So this sort of, and even Newton had qualms about this instantaneous force at a distance. How can things move instantaneously? How can you know information instantaneously across space? So, you know, but, you know, regardless of this kind of intuition that doesn't seem to make sense, the theory of gravity still had some predictions that ended up becoming true over time. But this instantaneous force at a distance, yeah, it couldn't be rectified with special relativity. So that's why Einstein developed his general theory of relativity with this warping of space-time, and yes, it is very difficult, and I don't pretend to be an expert on this at all. But what the things that it did support were things like there was a certain starlight that bend around gravitationally heavy objects, stars that shouldn't be seen, that could, because of the warping of time, it actually acted as like a gravitational lens, and so certain stars could be observed with this lensing effect. The Mercury's orbit was did not follow if you just use the mass of Mercury and the mass of Sun. It didn't follow. It had a very eccentric
How are we
orbit.
getting the masses of these things?
Yeah.
That's a good question. It depends on the object.
Let's talk about Mercury. How do we get the mass of Mercury?
So, and you're kind of that's a good question. Okay.
Yeah.
You would
I'll give you a hint. On flat Earth, everything that we talk about is measured physically. In the globe model, all your measurements are assumed.
Well, if you use the Kepler's laws of motion and you have a period and things like this, it'll fall out of the equation. But
you can make equations to describe anything you like, but
well, that's the difficulty of physics, right, is that you have to. Yes, you're absolutely right.
Well,
math can describe aphysical things.
Yeah, we can measure.
But the challenge of go ahead.
We can measure flatness. We can measure no curvature at distances that the ball requires there to be curvature, and we can measure it flat. But then, you know, the globe scientists, you know, mainstream science, they assume a radius of the Earth. With that, they determine the size and distance of all of the other planets and stars, and all of that is made up on an assumption. Nathan, you want to show something?
Yeah, it's just there's no independent variable in that experiment that you as a researcher manipulate. You actually can't get one from the sky. So that makes cosmology, astrophysics, astronomy not science. Those are simply observations. And so you're not doing science when you look at the light bending from a star. But what my friend Sweld here recorded on the last eclipse was during the moon eclipsing the sun, you can see all the magnetic field lines generated from this interaction with the sun and the moon. This was not calculated in that test in the 40s. This was not calculated in that prediction. They negated all of this and said there's no magnetic interaction between the sun and the moon. It has to be the bending and warping of space-time. So again, that's pacing and leading. That's simply neuro-linguistic programming, bro.
No, but this image is hard to see, but I also, I mean, the sun has a magnetic field. There was no discrepancy with the sun's magnetic field.
Can you see it better?
Yeah. And then what makes you say that this is a magnetic image?
Well, what we see here,
because you can't see a bar magnet's magnetic field.
It's a perfect. You see this right here, a ferrule cell. It has the same magnetic field lines as you see during the eclipse right here. So I don't know. We can duplicate it. Can you duplicate these magnetic field lines with gravity? No. Can you bend this light on Earth with gravity? No. That's why they had to look up to the sky and say they were doing science with gravity, because they can't even do it here on Earth, John.
So when you say that we don't have any evidence, I mean, the light itself carries lots of information. That's how, I mean, the internet works and everything else, right? So you can do a lot with just observing light and determining like spectrum and spectroscopy, the shifting of the spectrum.
Let's talk about spectroscopy for a second. If I can say the word, spectroscopy.
That's fine.
Is they're claiming that they can tell what these lights in the sky, what gases they're made of. I've yet to see anybody do spectroscopy on a mile. If I had a garbage can filled with a gas and it was a mile down a flat road, and you had the best spectroscopy equipment in the world, I bet you if I opened the can of the lid of that garbage can, you couldn't tell me what gas is in there. But they want you to believe that you can tell what gases are on these lights in the sky that they say are trillions, hundreds of trillions of miles away. I mean, John,
it's pretty impressive, right?
Yeah, it was pretty impressive. It's pseudoscience is what it is. It's a belief. It's a religion.
Okay, well, so okay. I mean, you don't have a direct path of light from the garbage can to just some mile, like random mile on Earth, right?
Sure.
So, I mean, there's obstructions.
Let's go. We can do it we'll go to the Great Salt Flats in Bolivia, and we'll just go a mile. There's nothing in between us. We can do it over a frozen lake or frozen reservoir and do it. I don't believe that you could even tell.
I have a question too.
So I would say that yes, you can do that, but it's just impractical and it doesn't make sense. Yeah.
Good. Go ahead, Nathan.
The sensor, is it frequency dependent sensitivity to the sensor? So basically whatever you're measuring has to be the only thing you're looking at?
In terms of taking a spectrum? In
the lab frame, when they do it, whatever they're pointing it at, that has to be the only thing they're trying to measure.
So I have taken spectroscopy measurements in the lab. Okay, so I do have some experience with this, and in the lab, it has to be anything that's in between, anything that the light goes through, you're going to be measuring.
So they do it in nanometers in the lab frame, right? That's the distance they
have different sizes, but I mean, it's usually a micron, 10 to the minus 6 meters beam width, but that's the beam source. Okay, and there's different things. There's different methods of spectroscopy. So if you're trying to find a material and you want to figure out like what light it's absorbing, you can transmit light through the material, and then you measure out the corresponding light.
You're saying
if there's gases, if there's air, if there's water on the surface of the material, if there's any sort of gases, let me get to it.
Yeah.
Okay, because I know what you're gonna say. If there's anything that gets picked up, okay. So what do we do? So we just say we can't measure spectroscopy? No, you take a baseline measurement, and then you take and then you put your material in, and you take another measurement, and then you normalize out the background. And it's the same thing you do with the sky. You would take a baseline measurement, point it at black space, and then you take a measurement of the star, and you just normalize out. So any contribution would be from the star, and anything else would be just
all of our atmosphere, all the layers, all of the pollution, all of the gases.
It absolutely
all of the stuff in our atmosphere. We can just we can just take it out, and we can get a reading from that star that's hundreds of billions of miles
away. Carbon dioxide in the atmosphere, it absorbs light at a very specific wavelength and frequency. So anything that it absorbs, you wouldn't be able to see that light from the star.
And for John, absorbs specific spectrums of the electromagnetic energy.
Say again?
Oxygen and ozone. Those are the four main things that cause attrition of electromagnetic energy. And you're saying you're just blasting this, or you're just reading this signal that's blasting through the ionosphere, all the gas above our heads, which is inhomogeneous and anisotropic, and God only knows what chemicals were released that day in between you and the stars. Not to mention you have interference from all the other cosmic radiation, from all the other stars and all the other planets, and you're claiming to just be looking at one thing in the sky and measuring one thing in the sky, but everything is interacting with everything else if we're in space and light is traveling in all directions.
So you can see it's not opaque, right? The sky is not opaque.
No.
You can see, right? So there's visible light that you can see through.
But
right? There's regions in the spectrum that are getting through. It's not absorbing everything, right? If it's absorbing everything, then you wouldn't be able to see the stars at all, right? So when you have a telescope, you point it at a single planet, a single star, right?
And
all that light is
there's no other light
focused.
crisscrossing. There's no other light getting in that way. Like when I have a light, it spreads out in all directions. So there's light coming from every direction. There's all sorts of stuff in our atmosphere, right? All of this stuff is just interfering with it. You're saying it somehow it just says, nope, ignore that, ignore that, ignore that. I want the light from that star 100 trillion miles away. I don't.
Okay, so
I believe that's pseudoscience.
Me too.
If you take a telescope and you look at the planet, you don't. I mean, you can see the planet.
You're looking at whatever you're looking at.
Instead of your eye, you put the spectroscopy instrumentation on the back end, and it focuses the image. That's the light, and you just take a background image and you take it out.
You're assuming that these stars are hundreds of trillion miles away. The planets are rocky balls or gassy balls or whatever they are, floating in a space vacuum, which is impossible. But we'll just say gravity holds everything together. What if you were actually looking at a light, not claiming what it is, that was only very close, that was very close, very small and very close? How would you know? Like if you're looking at, you say, okay, that star is, Betelgeuse, and it's, 1,000 times bigger than the sun or whatever it is, right? Or that's another light that's, a million times closer and a million times smaller. How would you know?
That's a good point, Dave. I actually think it would be easier to do on our model than their model.
Right.
Looking at stars and determining what they are using the frequency.
Well, you guys can do it.
Yeah, but we can do it. Like the stars that you're looking at, John, you have to understand, you can see stars with your naked eye, right? You can see stars with your naked eye.
Yes.
So do you know that your eye has an angular resolution limit? You can see a penny if I held it right here, but a penny is at 200 yards away. You can't see it. Its angular size is too small. Whatever the distance is, I forget the equation. But things get too small to see, right? So our sun,
absolutely,
sun, 186,000 miles across. If it was a mile over your head and you went outside and looked up, it would fill the whole sky, right? 186,000 miles, it would fill the whole sky. Then we move it 93 million miles away, and now it's the size of a dime or a nickel held at arm's length, right? Just like we see it. Mm-hmm. So it reduced in size, 93 million miles away, 8 light minutes. Okay. If I doubled the distance, it's going to get a lot smaller. Nathan, is it half as small or 1/4 the size?
Half.
Okay. So half. So when we go half, now we're the size of maybe a pencil eraser, maybe a little bigger, right? So that's twice the distance. Now we go 4 times the distance. It's now pretty darn small. 8 times the distance. It's now the size of a star. Okay, we'll call it a big star, right? At 8 times the distance, 8 times 8, 64. We'll call it a light hour. At a light hour, our sun is very small. Let's go 2 light hours. It's tiny. 4 light hours, 8 light hours, 16 light hours, a light day. At a light day away, if you do the measurements, you could not see our sun, the size that they tell us it is, at 1 light day away. Just stick with me for a second. Stick with me. Okay. At 1 light day away, you could not see the sun. Can you see Polaris with your naked eye? Answer is yes, you can, right?
Yes. I mean, I saw it a couple nights ago.
Yeah. And so Polaris, they say, is 46 times bigger than the sun. So if at 1 light day away, we can't see the sun with our naked eye, if Polaris was 46 light days away, you could not see it. It's beyond the angular size that I can handle at 46 light days away, right? Let's round that up to 2 light months, 60 light days away, right? You definitely can't see it. Let's round that up to a year, right? 6 times farther than that. You definitely can't see it. They tell us Polaris is 433 light years away. Where's the point where we're going into Narnia nonsense pseudoscience world? It happened right away, actually. but how far do I have to go? So you believe that you can see something 433 light years away that you couldn't see it 2 light months away. And I'm giving you the benefit of the doubt by rounding up to 2 light months. And then you believe you can point a thing at it and say, oh, that's made out of this and that. How about if that light was just a few miles up and you're looking at it and taking some measurements and maybe there is some accuracy to it? Maybe, I don't know. Nathan, what do you?
Yeah, 433 light years away. How's that thing tethered to the Earth for at least 50 years? They built the Georgia Guidestones 50 years before I showed up and took this time lapse. And all the stars rotate right up around this little oculus. Polaris was the only star you could see in this hole. And you're saying from 433 light years away, 50 years later, it's still through this one hole, bro. And you'd have to have gravity pulling on everything, not just in our solar system, but pulling on everything near Polaris. Somehow Polaris maintains some sort of like tethered vector directly above Earth's axis, or the Earth is just stationary. And that's
John, let me just throw something
okay.
out there.
I would like to address your
no, I'm gonna let you go. I want to go to you are familiar with the Georgia Guidestones? Yes.
To be honest, no.
Okay,
I'm not,
that's why. Let me just throw it out real quick. There's
you.
a monument that was built in 1981 down in Georgia. Very strange story behind it. That's a whole nother podcast. And it has it's a calendar and a timepiece. But through the center stone, there's a little tiny hole, and you could see Polaris through it. Okay, and so Polaris stays in that hole all year, all the time. Right now, they tell us that the Earth is wobbling. And that, 2,000 years ago, it was pointing towards a different star, Thuban or whatever. And in 2,000 years from now, we'll point to another star. But we're happened to be at the time where Polaris is lined up. They lined it up with Polaris. The problem is it was up for over 40 years. The Earth wobbles at 1 degree every 76 years. So that's more than a half a degree. It would have moved out of there. A half a degree is 1.5 moon widths. And so it would not be there, but it was still there. And then after Nathan made that observation and we started making videos on it and they started going viral, do you know what happened to the Georgia Guidestones? They just, a terrorist blew them up, right? Out of nowhere, boom. And then within hours, bulldozers were there, took the whole thing down. There was no investigation ever. You know why? Because that was rock solid proof that the Earth is not wobbling and that space isn't spinning out of control.
Also, it said on the Guidestones that they wanted to reduce world population using pharmacy and, big pharma. And so that's another reason to tear it down. What was going on in 2020? Well, they were making everyone wear masks and telling them to be afraid of parks and beaches, but Walmart and McDonald's were fine to visit. So, I mean, we got to open our eyes, John. I just want to say you got a ton of courage inviting both of us up. And
yes.
Pleasure to
well,
talk to you.
I do like to, face the controversy and I don't like to censor things either. That's like, I'm very anti-censorship. And I mean, that's why, our previous debate got lots of, very passionate.
And listen, and I want to apologize for some of the flat earth comments that will come on this because flat earthers get really passionate. Listen, you're a good guy. I think you want to know the truth. I think that you studied hard in school and memorized a lot of stuff. Okay. And you did. I can tell. I know that you did. But let's stick on what we were just talking about a second. The angular size of the sun at 2 light hours away is impossible to see. The angular size of Polaris at 2 light months away is impossible to see, but we can see it. You have to address that.
Okay, I'll address it. And this is, I'm not an astronomer, but
you don't have to be an astronomer. This is basic. This is
okay. Well, okay,
size.
but okay.
Yeah.
Let me counter with something. You had mentioned a penny, and that you can't see a penny maybe like a mile away or something like that.
Something like that.
Sure. So what would be what's the aperture size of a laser pointer? Probably smaller than a penny, mostly, right? But if you're like standing on a mountaintop with a laser and someone's at the base of the mountain, you certainly couldn't see a penny at the top. But if they're shining a laser pointer right at you, or even in the surrounding trees, you'd see it, right? You'd see at least the light, right?
Is Polaris a laser?
It's emitting radiation.
It's emitting light, and the light spreads out in all directions. And so as it
what
spreads out of all directions, what happens to it?
It attenuates, or
Yeah. It spreads out.
Whatever intersects at that. I mean, it all irradiates outward.
Let's
call
dimmer,
it a sphere.
It gets dimmer and dimmer as it spreads out.
So, but at least a mile up the mountain, you can see a laser, the light radiation from a laser, right? I think we'd all agree.
A laser is analogous to a penny. A laser is like a focused beam of light.
Well, exactly. That's why that's the difference, and that's why there's a difference with the stars as well.
Right. So, but they're not focused beams of light. They're just light that's attenuating in all directions.
What's the power output of that laser? What's the power of that light energy? Usually, you can look it up on the side, and it's usually 5 milliwatts. 5 milliwatts. That's 5 divided by 1,000 watts of power. The sun. I mean, even a solar rooftop has it usually has like 500 watts or so, and that's just like a small panel, and that's only absorbing a small fraction of the spectrum of the sunlight. The sun, according to scientists, again, I'm not a heliophysicist. I haven't done these experiments, but the sun's estimated to have power of 10 to the 26 watts. That's huge.
It is, and you also have to believe that the sun is burning 160 million tons per second or something stupid like that of fuel, and over billions and billions of years, it hasn't gotten any smaller. You have to believe that it's burning all this. Last time I took a bag of hydrogen and lit it on fire, it exploded.
When did you take a bag of hydrogen and light it on fire?
Saying,
That's probably not a good idea.
In theory. In theory. But in space, a vacuum with gas that decides to collapse on each other rather than fill the available space, it's burning 640 million tons per. I think the number's so stupid I can't even remember. It doesn't matter what it is. It's burning that constantly all the time, but it still doesn't shrink. It still doesn't shrink. And it takes 500,000 years for a photon to go from the middle of the sun to the end of the sun. Again, we're in pseudoscience make-believe land.
Well, so I guess like the one of the big premises of physics, and I think perhaps this is something you guys could agree with as well, is that energy is never created or destroyed. It just converts to one form to another, right? So the physical process going on in the sun is the fusion, which is turning hydrogen into helium, so that the particles are still present in the sun. But you're right. I mean, eventually there will be it will run out, but it's going to happen a lot longer than the course of our lifetime.
Hang on one second. Dave, do you want to make a comment on that? Because I have one thing I want to say.
I want to talk about thermal conductivity, but go ahead, Dave, because the center of the Earth is as hot as the surface of the sun, right? So that heat would radiate out faster through the solids than it would from a gas in a vacuum. And you'd actually experience more heat from the center of the Earth than we would from the sun because of thermal conductivity.
That's an interesting point, and it's something that it's definitely worth thinking about. But I mean, the vacuum of space. I mean, it is cold, so there's a thermal gradient.
So here's the thing: you're making so many assumptions. All of your stuff is based on that space is a vacuum, that the sun is thermally nuclear, burning hydrogen in a vacuum without a container. I mean, these are things that break the laws of physics. But the only thing you can throw in there is gravity. Gravity holds the sun together, right? That's why it doesn't expand into space. Just tell me if that's your belief. What holds
the gravity?
The sun's made of gas. Why doesn't the gas fill the available space?
Well, plasma.
Okay. Why doesn't the hydrogen and helium, which is 99% of the sun, fill the available space? Is your answer gravity?
The answer is gravity. Yes.
Okay, so how much gas do you need for it to collapse on itself before it, instead of expanding into space violently?
At least as much as the sun has.
Yeah. So because the sun is a ball made of gas in a space vacuum, therefore it collapses upon itself. That's circular reasoning.
Well, sure, but.
It's
not the sun's not the only.
The sun's not now all the other stars, and because all of the other stars are gases, and they've done that, then therefore it's true. Again, you're making an assumption.
Okay.
That the
So
sun
how
is
about
even
this?
a
How about
physical
this?
object.
So obviously, no one was there to witness the creation of the sun or the Big Bang or anything, right?
I was
What
there.
is your idea of the creation? Where things? I mean, and I don't necessarily want to get off on any like religious topics or not, but and if you don't want to talk about it, but
You
like
know what? I'll let Nathan throw in his.
where do we come
that.
from?
What? That's a great question, Nathan. What? Go ahead, give him your short answer.
Bro, I used to run the largest flat Earth research group in human history, so I didn't jump on podcasts to tell people what I believe. I wanted to do this to talk about what we could prove, what we could verify, so we could figure this out ourselves. And if you want, we'll talk, bro. Send me your number. But let's do that off the podcast. I'd like to eventually get to curvature of the Earth. But while we're talking about space, John, I'd like to know if you could demonstrate here on Earth a gravitational orbit.
Like satellites or a gravitational orbit?
Yeah, and in like the lab frame, can it be demonstrated, or are we just trusting the government when they say what they do with metal boxes is gravitationally orbit the Earth?
So to get something in orbit, you have to have a sufficient velocity to actually achieve orbit. It's because of the way the inverse square law of gravitational forces. It's you get less velocity the farther away you are from the center of the Earth. So, and on top of that, to have an object that is sufficiently fast to get into orbit close to the surface within Earth's atmosphere, you get significant drag, which reduces the speed. So it's not feasible to achieve an orbit within Earth's atmosphere because it's just operationally prohibitive based on the air drag. That's why rockets they lose their booster rockets. They have to get the most fuel, the most thing that they go through is lower Earth's atmosphere. It's the most significant drag during the rocket launch. And then as they get past the queue, then they drop the boosters and they just rely on they drop mass and they get sufficiently high so that the orbital speed can be achieved. And that's
but you could recreate this, John, without all that air resistance. Is you just show me a gravitational orbit in a vacuum. You know what I mean?
Because you're putting this in a large gravitational field of Earth.
Right.
So basically, we can't demonstrate the mechanism by which the ISS orbits the Earth, can't demonstrate the mechanism by which the government tells us satellites orbit the Earth, which all the planets and moons orbit the sun in reverent obedience. Can't be demonstrated, but it works. It works, trust us.
But the reason they can't demonstrate it is because you need gravity, and you need something as big as the Earth to demonstrate the gravity. I'm going to take John's side on this one. You can't do that because it requires something as big as what we're on. But I have to ask you a question. An orbit is, so I got a satellite right here, and the reason it doesn't fall to the Earth is why?
Speed,
because it is falling. It's falling. It is free falling, but its drop is equivalent to the drop of the Earth. So whatever height it is, it's going the proper speed to maintain. So it does. So its drop matches the orbit of the Earth, right?
That's right.
So a geostationary satellite. So we got Australia over here. We got a geostationary satellite. The Earth is spinning. So that satellite is just going perfectly with the spin of the Earth, right?
Mm-hmm.
And it's
falling. That's the way it works.
Yeah, but the Earth is also orbiting around the sun, speeding up and slowing down in an elliptical path. Okay, what changes the speed of that satellite? I mean, how does it know that the Earth is speeding up now? It's getting towards December, I think it's December. It's going faster. It's speeding up and slowing down. We're chasing the sun in another curved path. We're spinning, but somehow that satellite matches all of those motions, right? And it's falling. So let me ask you a question. John, if you drop something in a vacuum, does it reach, let's say we have a bottomless pit vacuum, and I drop something in it, will it speed up infinitely? Because there's no air resistance.
Yeah, well, if there's something pulling it down.
Well, gravity. Something's falling due to gravity, and there's no air resistance. Does it reach a maximum speed, or does it continue to speed up?
It would continue to speed up.
Of course,
I
that
assume.
is what your science says, and us flat earthers, we agree. Everyone agrees with that. So in space, is there resistance? Is there air resistance?
It's not really.
There's no air resistance. There's no air. So
Yeah. I mean,
the
it's very
satellite,
low.
so the satellite is falling without any air resistance. Why isn't it speeding up?
Well, there's a restoring gravity. I mean, what's the forces acting on it?
The gravity is acting
That's
on
right.
it. So
That's
I
right.
throw a baseball and it goes as far as I can throw it, but it's falling the whole way as it's going. If I threw it level, it's just going to fall due to gravity. There's no air resistance, right? The satellite would be speeding up constantly. Now, you're not going to be able to answer this question because it destroys the idea of an orbit. You're not going to be able to answer it because it completely destroys your world belief of orbits. And if you break up orbits, satellites, ISS, planets, all of that, everything falls apart.
So look, if you have an object and it's orbiting here.
What's an orbit? It's falling around.
Okay, but there's still a force of gravity acting on the object.
Gravity is pulling it down. Okay.
Okay. So in the example that you previously mentioned, let's say like an infinite long tube, and there's just some gravitational force acting on the object, right? So that the direction of that force is always down, right?
Sure.
So it'll just continue accelerating in that same down that path. If you're orbiting, if you're on this side, the force of gravity is pointing this way. If you orbit here, the force of gravity is pointing this way. The force is changing constantly with the orbit. So when you have a constantly changing direction of force, you maintain a constant speed.
I don't know. I could actually agree with John on this, that the change in direction could constitute the acceleration, and in their world, kind of compensate for what you're trying to say. Because it's constantly changing direction. So it would have to be constantly accelerating, which we should feel, by the way, John, because it's changing direction. Just the same way if you were in a car, NASCAR, turning a loop at 80 miles an hour, you would feel that constant outward centrifugal.
Okay, let's talk about that. Because you're absolutely right. You would feel if you're going at 80 miles an hour and you make a right turn, you're going to feel some acceleration because the change of the direction, right? And this is a common flat Earth criticism of the globe model. Why can't we feel? I mean, we're spinning so fast and all this, right? But when you make that right turn at 80 miles an hour, how many seconds are you making that change in direction? Or minutes?
You could do it for an hour. You'll feel it the entire time.
But okay, they have trains. They have like passenger trains with dining cars. And they serve food and drinks, and those tracks aren't always straight. So how are they not spilling food all over the place constantly?
Well, the tracks are pretty darn straight, and when they do turn, the train tilts a little bit for that turn and keeps everything pretty nice. But you're also in an enclosed car.
They slow down for the turn slightly too if they're going around a
if it's a sharp turn, they'll slow down. Sure.
Yeah. Sure. But if let's say you're in a car and I mean, on a highway, those don't always run straight.
No, absolutely. You feel it. You feel it. Yeah, but you normally have a top on it that has sidewalls. Get a dinner plate, fill it with water on the highway, and take the slightest turn or the slightest change in acceleration, and the water will come right off the plate.
So the thing that matters here is the time, how fast it changes.
So the Glober argument is watch the hour hand on a clock. You can't even see it moving. And that goes around. That's only going half the speed, half the angular speed, right? Is that right? Or no, it's going twice the speed because it goes around twice in a day. But the truth is if you're on the equator, you're going 1,000 miles an hour. You're deviating to the right or the left or whatever direction you want to call that at like a mile per minute. You would feel that.
But angularly, you're taking 6 hours to make a right turn.
It doesn't matter. You know the SR-71 Blackbird, for example, the SR-71, the spy plane, right? It goes
Yes.
2,300 miles. Is it 23 or 30? 2,300 miles per hour. All right. And that when it's going that speed, it cannot change directions. 2,200 miles per hour, right? It cannot change directions. It only can fly straight. It can't turn left, right, or anything. Now think about that, because it'll break apart, right? But if it doesn't go down, it's going to fly off into space, right? Do you know how much it would have to go down every second just to follow the curve of the Earth at that speed? 80 stories, 800 feet per second. What would that do? So they're going, and they have to nosedive down 800 feet per second. What would happen to the pilots? They'd be smushed against the ceiling. Right.
Yeah.
But they don't. They fly straight and level. Airplane.
Also,
I'm not sure but I mean, yeah, go ahead.
While you have that image up, Dave, I just wanted to point out there's an instrument on board the airplane called the attitude indicator. It uses a gyroscope. And the reason it uses a gyroscope is they keep their rigidity in space. So once you start that gyroscope up on the tarmac and you take off, that gyroscope is going to resist the forces that try and change it from that plane of inertia that it's spun on. And so if we were going around a globe, the gimbal base would change its orientation relative to the gyroscope, which keeps its rigidity in space because we're going around a globe. But you can be on a 12-hour flight from here to Korea, here to China, here to Japan, and the gimbal base does not change its orientation at all. And the pilot actually flies straight and level the entire time, other than the ascension and the descension of the plane. The FAA admits that in the documents when they train the pilots, it's flat, non-rotating, and they actually negate a gravity vector. So airplanes, are exclusive.
And one other thing I want to throw in there. When a pilot is when you're getting close to the airport, you're 30 minutes away or whatever, the pilot has to calculate the rate of descent. It's like, okay, we're 100 miles out. I got to go at a 3 degree. I got to drop X number of feet per minute to get there. They do not calculate the curvature of the Earth. So at 100 miles away, if they calculate the rate of descent, when they get there, they're going to be a mile higher than they thought of. Because at 100 miles, there's over 6,600 feet of curvature. So they're going to be an extra 6,600. They're going to miss the runway by 6,600 feet of altitude because they're not calculating in that extra drop of curve. They're only calculating on a plane, on a flat surface. Can you address that?
So this is an interesting point, but it does refer back to gravity. So
there's no gravity. There's no gravity. That has nothing to do with.
So there's still a gravitational field from Earth.
Doesn't matter. We're not talking about gravity. We're talking about that. Like if I'm looking over at my floor over here, I can point and I can say, all right, I know what angle I have to do to hit the corner of my floor over there. But if my floor was curving, I would have to angle lower to hit that spot. I would have to, if I'm looking at a ball, right? I want to go from here to here. I'd have to calculate that I'm going down here. I'm going from here. I'm flying down to there. But if it's flat, it's a whole different calculation. They use the flat calculation. Here's something a pilot told me. If they treated their flight plans and their calculations as the Earth was a ball, they'd all be dead.
Well, I think the gravity self-corrects the flight path, though. I mean, because
where did you get that information from?
Well, just thinking about the forces acting on it. I thought about it. I mean,
you need that to hold on to your religion.
No, but I mean, it's true because if you deviate up, if you're just going away from Earth and the force of gravity, you'll just go out into space, like you said.
What
are you pushing up against?
I'm 100 miles from my location, and I say, okay, I'm at 30,000 feet. I have to divide 30,000 feet by 100 miles and realize I have to drop X number of feet per mile. How come I'm not calculating in curvature? Because there's an extra mile of curvature from that distance. How come I don't calculate that?
Because I mean, it's just like a parabolic thing. It hovers. You have a force of gravity acting down the whole time.
Gravity, schmavity. Let's say there's no gravity. It doesn't matter.
Then you would definitely have to keep curvature into account.
The angle of attack, the angle of the angle to the airport, to the ground. and they're not calculating in a curved ground. They're calculating for a flat ground. Why don't they calculate for a curve? That's a mile of curve, over a mile.
Is the height so the altitude doesn't change, right?
No, you're at 30,000 feet, 5 miles, whatever it is. Okay, and you calculate how many feet per mile that you need to drop to get to the airport. But if you don't calculate the curve of the Earth in, you're going to be over a mile too high when you get there.
So, I mean, again, I'm not a pilot here, obviously.
You don't have to be a pilot to understand simple calculation. It's a
no, but here's. I mean, look, like if you're going along a curve at a constant height, you're not changing altitude, so you don't have to take. You're only at like a certain height, and you have a gravity acting down. So the gravity keeps you at a constant altitude. I mean,
John, gravity gravity is your god here. Let's not say the word gravity again. I'm going to ask you. I'm going to state it in a different way.
Well, if there's a explanation that doesn't merit it, I won't say it again. But
well, if I'm 10 feet in the air,
I just don't understand how you can't accept gravity. Like, I don't understand. Like, what do you think pulling everything down? It just doesn't really.
Well, because you can't prove it, you can't measure it. They've already discounted it. They changed it to the bending and warping of space-time. Nobody knows what that means because it's just silly. And the electrostatics are testable, repeatable, measurable, observable. They say it's 10 to the 36 stronger than gravity. Let me ask a question. If I was going to pull, like, let's say I want to pull your car and I'm gravity. I'm going to pull your car down the road, but Nathan's electrostatics. He's going to pull it the other way. Is my 1.00360.1 force against him going to make any difference at all? Zero. Going to make zero difference.
If he's charge neutral, it would.
All right, Nathan, go ahead. Excuse me.
Yeah, it's all right. I want to get to the horizon eventually because we're not pilots,
okay.
right?
Yeah.
You want to mention that when they descend, it's 1,500 to 3,000 feet a minute. And just at 500 miles an hour, the plane would have to be constantly dipping the nose down 2,500 feet, 2,700 feet a minute. So it'd be almost the rate of descension. You would have to curve the plane. And people can feel when the airplane is descending. As soon as you leave that straight and level path with the airplane and the pilot says, hey, we're approaching our descent, you start to feel the plane turning downward. And you would feel that the entire flight because you'd have to dip your nose. But yeah, the horizon. John, I'm curious. I don't mean to put you on the spot. Do you know how far the horizon would be for a 1 or a 6 foot observer if the Earth has a radius value of 3,959 miles?
We had this last time, but I didn't remember the numbers off the top of my head. So
for a 6 foot observer, it's 3 miles, 2.99 miles. And for a 1 foot observer, it's 1.22 miles. Now, I could show you the horizon past 9.4 miles for a 1 foot observer. So that's way past 1.2 miles, right, John?
Yes.
Yeah, it's way past. Magnitude's past, almost 7 times as far as it should be. The problem is with refraction, if you invoke standard refraction, it changes the distance on surface from 1.22 to 1.34. And they've only met nature magnitudes of plus or minus 2 from that standard. So we can't just invoke imaginary amounts of refraction to make the distances work. If that was the geometric curvature of the Earth with no refraction at all, we'd be seeing a radius value of the Earth of 240,000 miles, which is the orbital path of the moon, John. That's crazy, bro. We see way too far. And let me say this real quick. If we don't see the curvature away from us, and we go up to 128,000 feet, and we don't see it left to right, where is this elusive, negligent curvature that fails to show up for its assignment every time we look for it?
You mean if we go up a mountain, or is that what you're asking?
High altitude weather balloons at 128,000 feet. Admittedly, by Neil deGrasse Tyson, there's no curvature left to right. And from Earth's surface, we should see the horizon at 1.2 miles. And I've got it past 9.5 miles. So we're not seeing it from our toes to the horizon. So what do we have to look diagonally across the Earth? Because it's not going away from us and it's not going left to right. Where is this curve, bro?
I mean, that's a good. I mean, I would say that spacecraft and satellites clearly see it, but I'm not so sure. Like, when did Neil deGrasse Tyson say we can't see it from a weather balloon? Because I think that's a little.
he was commenting on the Felix Baumgartner space jump, and he actually had a giant beach ball on stage in front of a college. And he says, you don't see the curve of the Earth from 2 millimeters above this beach ball. That stuff is flat. That's like word for word what he said. So, admittedly, no civilian has ever seen the curvature of the Earth, John. It's only the government. And notice how you went straight to satellites and spaceships. You're appealing to the government, which is the organization that's like promoting and pushing this whole entire deception. It's crazy.
Well, I think that's an extrapolation a bit, but I will admit that the curve is difficult to see on the ground. This is why it was a hard model to accept.
John, do you agree on a ball? Do you agree on a flat Earth that the horizon would be optical? That we can only see so far.
This is sort of what we discussed with the perspective of how horizontals.
So you agree that
limited...
that you can only see a certain distance until everything merges together, and that's your optical horizon on a flat Earth. On a flat Earth, if the Earth was flat. Crazy idea.
Yeah.
Earth was flat. Okay. On a ball, do you agree that there has to be a physical limit to how far you can see based on the height that you're looking from?
It would obstruct the other side based on the curve.
So on a flat Earth, you can see as far as you can see, but on a ball, like you can't see my mouth because it's behind a physical curve, and no amount of magnification will change that, right? Stick with me.
So this is I know, but I don't want to fall into a trap here.
No, it is a trap. It's
careful.
a trap that you have to face reality. Okay.
Well, look. Okay.
Hold on.
Okay.
If this is the Earth right here, and my mouth is this far over the curve, is there any way that you can zoom in on it?
No.
Okay. Very good. That's not a trap. It's very easy. That's just a lesson in reality. So there is a curvature to the Earth, 24,901 miles around. There's 3 or 4 formulas, and the one that gives the globe the benefit of the doubt is the 8 inches per mile squared, and that goes up to a couple thousand miles. But we're not even talking about a couple thousand miles. Let's just talk about 8 miles, right? Now, I think I showed you this last time, but let's just look at it again. And I really want to hear what you have to say. We got a camera 6 inches off the ice on a frozen lake. We have these 4 lights that are 8 miles, 7 miles, 6 miles, and 5 miles away. The curvature should be more than 30 feet, 22 feet, 15 feet, and 9 feet. But for some reason, we can see them all at the same level. Now, you'd have to believe that this one is refracting up 30 feet, 22, 15, and 9 feet, and they're all stopping at eye level to trick you to think the Earth is flat. Magical refraction is moving them all up, or maybe just the Earth is flat. Go ahead, Nathan. You want to say something? You want to add something?
Yep. Say at 1 foot, the geometric horizon should be 1.22 miles out. So just the horizon alone should be obstructing all those lights, let alone how much curvature we're missing.
All of those lights are behind this ball. My fingertips are those lights, and they're here. But some reason, you see them on a flat plane.
So this is a very interesting experiment. I would really like to see this done.
Don't do it yourself.
I need to find a frozen 8-mile lake somewhere.
And by the way, people say,
I live in California.
It's difficult to do these experiments. You got to go out. This guy went out.
Well, I know. I
driving his truck on the ice.
I applaud these kind of work.
Right.
And this is the kind of stuff that I do.
The work has been done for you. So you want to do it yourself because you want to verify this, but let's just assume you did this and you saw this. What would you say? So you 100% know there's no trickery here. If you did this and you saw this, would that make you reassess your globe belief?
I would likely try to find an explanation, but
of course you're going to scramble to hold on to your religion. What would that excuse be?
Like, what would be a potential?
I can steel man it for you if you don't have one.
No, well, I mean, look, like there could be there are like I know you don't like refraction, or it could be a reflection. It's an ice lake.
There's snow on that. There's snow on the ice.
Okay, but what are these lights like? How big? Like with the aperture
They're just
sizes?
lights.
And
They're just like lights like this big.
Yeah, they're one.
because
There's a whole
I would say
there's
the
a
one
whole
at
video
8.
on it.
I would say the one at 8 miles is definitely dipping down a little bit compared to the 5 mile one. But
No, it's just
again,
its light is attenuating a little bit. They're all there.
or
It's just
below the curve, like you said. I mean,
30 feet below the curve. 30 feet.
John, are you familiar with Rayleigh criterion? It's why
Rayleigh criterion.
as things get further away, like headlights, they'll converge into a single headlight. That's because the wavelength of light has become unresolvable. So, like, you can't put this light 80 miles away, 1 foot off the surface of the water and still see it. It's becoming unresolvable. And the way that would become resolvable is from the bottom up. That's how things would disappear on our flat Earth. And I just wanted to show you this real quick because we were talking about perspective a few minutes ago. These are lines of convergence going towards a vanishing point, flat horizontal line. If you just go here and you read about parallel lines of convergence, it'll say it's the point at which all the parallel lines appear to converge. Now you go here to Google and you say, can parallel lines curve? And it says parallel lines cannot be curved. So perspective is exclusive to a flat Earth.
And John, take a look here. So
Okay.
this is this a sphere or is it a square?
It looks circular.
It does look circular. I'm with you. It looks circular. And I usually ask people, is this the sun or is it the moon? And they're like, well, it's really hard. It's really hard to tell, right? But what this actually is, it's the front of a train. Okay.
To be honest, I thought it looked like a train.
Okay,
I
well,
wish you didn't say it. I promise you, I thought.
No,
it
that's
looked like a
okay.
train.
That's all right because it looks like it's a sphere, but as it comes closer, it doesn't even have a standard headlight. It has these other lights, different colors, different shapes, but you see it as a sphere, and that was like half a mile away, not even. So again, looking at the lights in the sky, looking at things and go, oh, that's a sphere, that's a planet, that's gases in a vacuum, which again, you didn't address how that happens other than gravity, and you need a lot of gas, circular argument, before it collapses upon itself. All of these things that you need to defend your globe belief, all those things they break the laws of physics, and you just have to believe them because they are. The Earth is a sphere because the Earth is a sphere, right? I'm going down because of gravity, and someone in Australia is going up towards me, which is down for them because of gravity, because we're on a sphere. This is all circular reasoning. This is all a belief system based on pseudoscience. It's your whole listen. This is I'm looking at your channel, Dr. John, your channel, looking at your videos. If you come to the reality that we're showing you, everything, all of your stuff is completely changed. I mean, most of it's destroyed.
No, it's definitely not. But it's also I'm still. I mean, like, I think the reason I like having these talks is that you press on some things that are definitely difficult to have. You pick up some observations that are very interesting and make someone think.
Okay.
Now, how can you benefit by knowing a little bit about physics?
What do you mean?
I mean, like, your argument, you kind of say stuff like, oh, that's like, it's this observation doesn't agree with physics, so therefore physics, it's wrong. Listen, but then you're already saying that physics is wrong. So like,
no. Physics
that's
is
a circular
real.
argument too,
no,
right?
there's physics, like the physics of my setup. I know how things set up, and I understand that. But then you get into pseudophysics, you get into pseudoscience and just stuff that's made up, stuff that has that's all circular reasoning. When you go there, then that's stupid. Globe believers, they say that what was I going to say? I had a good point, that it is because it is, and it's like, that's not. Oh no, it is because of physics, because of science. We love science. That's a word. Physics and science are a word. How are you using them? Right? It's like, how are you using them? Science isn't proof. Science is a word. Now you can do some science to show something. Where's your science? Where did your radius of the Earth come from? Because your whole world is based on that. Where did it come from?
Well, I mean, the original measurement by Aristophanes.
Eratosthenes.
You know.
Eratosthenes. Are you really going there? Didn't we talk about that, Eratosthenes? I'm going to show you Eratosthenes right now, and then you're going to have to get rid of that and never bring it up again, or you're being disingenuous, right? Eratosthenes said he did his sticks and shadows, right? He said,
Which,
Eratosthenes said that all the rays are coming in parallel. No one's ever seen parallel rays, right?
okay, but those are going through the clouds.
Well, it doesn't matter. How are you going to see the rays otherwise? Whether they're going through the clouds or not, they're not straight. But I want to show you. Hold on a second. Where is?
Yes, they are.
All right. So
because the phases of the moon.
What's that?
Anyway, go ahead.
No. What I'm going to show you is, so Eratosthenes said that where's I'm trying to pull up something here. Where'd it go? Where is 1 second here. Lost my
wow. I suppose I have to ask, if his assumptions were so bogus and wrong, then how was he so close to the real
first, did he even
circumference of Earth?
What circumference of the Earth? The one that he assumed, and then
it just turned out to be almost right.
How is it right? Okay, here's Eratosthenes.
It's within like 10% of the measurement we have today.
Where did we get that measurement from? It's circular reasoning again.
No, how?
Where did the measurement come from? First, let's look at Eratosthenes. Here's Eratosthenes. He's got no shadow on his stick. Here's his buddy 500 miles away. He's got a shadow. You can measure the length. You can do the math, and you can figure out the sphericity of the ball, right?
Yeah.
That's how it was done, right? First, and his buddy walked 500 miles and counted his steps. That's how he knew he was.
It was well, sure, but I mean,
okay.
To be honest,
and they knew that they knew exactly when to do the measurement, right? With no time issue, being 500 miles away.
It was a big thing over in Siam because there was no shadow. I mean, it was it was the solstice.
So here is a flat Earth. Here's Eratosthenes. The sun is directly above him. Here's his buddy. The shadow length is the same as the shadow length here. And you could do the same math and assume a ball because it's a ball. You could assume a ball because it is a ball, right? If you assume a ball and you do that math, you can say that this is spherical when it's actually flat. Right? And why are all of your best globe proofs from people that you can't even prove existed? Right? Why don't we do that today? Right? It works on a
yeah, you can absolutely do that today.
I know, but it works on a flat.
I mean, this is where sundials came from.
John, it works on a flat Earth perfectly. Right? Here I got these cans here. It works on a flat Earth with a local sun. It works on a flat Earth. Neil deGrasse Tyson even said it works. No shadow or very small shadow, long shadow. This is a flat table, but you can do math to say that table is spherical.
So that's, you can, his assumptions at the time, sure. I mean, he didn't, those were assumptions.
So you can admit right now that Eratosthenes' measurements work on a flat Earth.
Yeah, yes.
So they do not prove the globe. So where did the radius come from?
No, but from his assumptions, like for any theory, like if you have an assumption of a sphere, then I mean,
where did his assumption?
I mean, we have better measurements than that now. It's like there was actually.
Where did they come from? Right. This is Carl Sagan on Cosmos going. There's no shadow, but it only works on a flat Earth. I mean, on a globe Earth, because he bends it and says, look, we can do that, and then brainwashed everybody. But they're not looking at it. No one's mentioning a small local sun, just like we see in the sky.
So, I mean, my biggest thing about that is like if the sun's local. I mean, again, the power output is huge. How do you have this? Like, it would be scorching. Well, you question, like, it's crazy, but like, I mean, like it's got enough power to generate like solar panels and stuff. Like, how is that energy source.
Go ahead, Nathan.
Yeah, moonlight's measurably cold, so it's photoabsorbent. So the Earth's not constantly heating up and heating up and heating up. It's a closed dynamic system with no energy loss. It's like the push and the pull. That's where they got the yin and the yang symbol from. One gives, one receives. That's why they get referred to as the male and the female. But yeah, the sun is extremely hot, especially around the torrid regions. During the summer, you can't even walk around without shoes, and you pretty much have to stay in air conditioning all inside. I don't know how people did it back in the day. It is hot. It is very hot.
So, I mean,
The sun is sending electricity.
So how far away do you think the sun is?
I don't know. I mean, I can't go up there and measure. But let me ask you a question. Do you know how solar panels work, since you brought that up?
Yes.
How do they work? How do they make electricity?
It's a photovoltaic effect. Which,
that's a word. That's like science. But what is the photovoltaic effect? How does it work? I can steelman it for you. Your scientists don't know.
No, that's not true.
Yes, it is. They think that a photon...
Okay, now you're speaking for me, but it's not true. How can you tell me I don't know? I mean, it's an atomic transition.
Because they think...
And it's a very specific band in the spectrum. Are you going to tell me, a condensed matter physicist, that I don't know what a photovoltaic is?
No, like, you know what they told you what it is, but they...
no, I've actually made these things.
You can make them
from scratch.
Yes,
from crystals.
I was in the solar power business for years. Yes, I was in the solar power business.
Oh, really? You know a lot about crystals?
I know a lot, not a ton, but...
Oh, yeah, not a ton. Exactly.
John, let me explain what the scientists say. They think that a photon knocks out a boron molecule.
What, are you reading this from flat earthers now?
No, this is what science says. Like when I was learning about solar power long before flat Earth, they think.
How do you think they make solar panels? How do you think they?
It doesn't matter. You can make.
Oh, it does. It actually does.
Why does it matter?
Because that's the science. Like the science is the material.
Science is
science is the material.
Science is the material. What is that?
Do you know what kind of crystals they use? Do they use silicon? Do they use germanium? Do they use arsenic?
It depends on all of
it depends on the energy levels.
All of those ingredients are in there. So, but if I can finish what I'm saying, they say a photon knocks out a boron molecule, and then an electron fills it in, and then it keeps doing that, and all of those are channeled, and they bring them together, and they create a current. Right? It's this whole thing, but they don't understand. Hold on. They don't understand. It's just a theory. It works, therefore it must be real. Okay? It works, therefore they must be right, because no one in that field is thinking that the sun is literally sending electricity to Earth, and those photovoltaic cells are collecting the electricity. That's it. They're just saying it's so simple, but they can't see it because they're blinded in their heliocentric religion.
Dave, how about I make you a challenge?
Okay.
How about you build a photovoltaic cell, an operation, and then we can talk about photovoltaics.
If you build
if you think it's all just black magic.
No, I don't think it's black magic.
They just get lucky sometimes.
No, the official description.
You know how many elements there are?
The official description.
Can you make it out of uranium?
The official description on how a photovoltaic cell works is a theory. Okay?
I didn't say that.
No, I'm saying that. Right? But it's just there's electricity, measurable, testable, coming from the sky, and the photovoltaic cell is picking it up. That's all it is. It's very simple.
It's so simple you can't make it.
I don't build things like that. No.
Oh yeah, because you don't know the theory.
No, you know the theory. Listen, I have a theory that the Earth is a globe, and I can put a stick out there, and my buddy 500 miles away.
Let me ask you, what does this theory say about which elements you can use and which you can't? It's so simple.
In what?
Well,
to make a photovoltaic.
Dave, he was like real touchy on the solar panels. Like, yeah, I don't know how it's so heated there.
Yeah.
It's all right.
It's because you're just guessing and you're putting words in scientists' mouth.
No, I'm not. I'm
actually
taking their words.
I've like an experimental person and has actually done this stuff.
You've built something that can create collect power from the sun.
For you to just like blanket statement stuff
No,
about
I'm
it is
I'm
just
not.
like it's
You
absurd.
you need to do a little research to understand they don't understand how they work. They have a theory and it works. Therefore, their theory must be right. It's just like
It's built up on everything else. Like
I
it's a
can't help you if you
universal.
can't see. I can't help you if you can't see that. I can't help you. Listen, we can agree to
I
disagree.
mean, I can't help you either because
Oh,
you just like kind of guess at what
no,
scientists
no,
are
I'm
doing
not
without actually
guessing.
being one.
I'm actually looking.
Do you read the research papers? Do you know what papers? What paper are you referring to? That's like just like
go show
blowing
me
your
the
mind
paper
right
that
now.
says they absolutely know how they work. They have a theory that it's knocking boron molecules out and electrons are filling the space. That's not what's happening.
That is not the it's not just boron. I mean that's you you don't it's not specific to that element at all. That's an example of one that works. I mean it's just like how do you think they design this stuff? Just sloshing stuff together and see what sticks? Oh, I think it went mute. I can't.
You could design things, they have a wrong theory and it works. You could make an assumption, hey, and it works, right? That doesn't mean your assumption's right. There's other things that could be happening that you're unaware of. The reason that the photovoltaic scientists don't look at what I'm saying is because they think they live on a globe and the sun is a burning ball of gas 93 million miles away. When in reality, if they realize that the sun is here within our system and it's electric in nature, then they would be like, oh, why didn't we see that in the first place? Because it's right in front of your face. The flat Earth is right.
I guess like taking a step back here. My biggest complaint with flat Earth, and this is where I draw the line on the skepticism argument, is that there's absolutely nothing productive about it. That there's nothing you can do that's going to produce anything better than a solar panel or a missile or a spaceship, an airplane. There's nothing that is productive from believing the Earth is flat. You can't gain any insights into predicting solar events, solar eclipses, orbital motion. You just say, I don't know.
That's not true. Go ahead, Nathan. I know you want to chime in.
And it's frustrating in the sense like
you're putting words in our mouth. You're saying things that we say, but we can answer that when you're ready.
It's kind of like going to it's like if you have a problem with your car and you just it's making a weird noise and you take it to a car mechanic, and because you can't fix the car yourself, but you see it's a problem, and then the car mechanic says, well, you need new spark plugs, and you go and you just say, no, that's not the problem, it's not the spark plugs. And then you go to another mechanic and they say it's the spark plugs, and you just say, no, it's not the spark plugs. I don't know what it is, but it's not the spark plugs. And so you see where this goes.
True.
I mean,
no, that's a horrible analogy.
You have lots of things that you don't have answers to.
That's not what we do. And that's not what we do.
Okay.
You have to let us talk for a second. You have to let us talk for a second.
Okay.
You say we don't have answers. Yeah, there's some things we don't have answers to. You make up answers to your stuff. Your stuff is based on nothing scientific.
It's a cohesive theory.
What's a cohesive theory? The globe?
And by the way, I mean, you said I make up stuff. I mean, the laws of physics are universal. It gives a framework for understanding
gas expands into available space. That's a law of physics, right?
Yes.
Okay. How does the gas stay on Earth, and how do stars form?
Well, we already went there, and you don't like the gravity answer, but that's the answer. But here, I mean,
when you're ready, Nathan has something to say. When you're ready,
exactly, like by teaching children about flat Earth, like what opportunities are you restricting these children from having? I mean, they just you're totally blindsiding these people from like being able to reason.
Yeah, by teaching kids flat Earth, we stop them from becoming astronauts and politicians and
effective engineers making like six-figure salaries. Yeah, I know you're really screwing up people's lives.
Yes. All right, Nathan, go ahead.
Yeah, you're basically Like, oh, the globe gave us cell phones, so it must be a globe. And the psychopaths up top are building missiles, so it must be a globe. And I just don't understand that reasoning. Tesla said the Earth was a Tesla motor, and that's comprised of stator, rotor, and magnets. So the Earth would be the stator. That's why he called it the stator, because it's stationary. The sun and the moon would be the magnets, and the sky would be the rotor. And so there's plenty of things. The way we're talking to you is through technology developed by flat earthers, people who knew Einstein was off. Okay, well, that's debatable. But we do plane surveying, assuming the Earth is flat for 100 square miles. So we build canals, railroads, bridges, buildings, all on a flat Earth. That's what we can do with a flat Earth. What my question to you is, like, because you said, oh, we take it to a mechanic, deny the mechanic. I tested the Earth for 10 years. I've been on National Geographic. I've been on Netflix. I started the largest flat Earth group in human history. I am the flat Earth mechanic. So I'm curious, what has globe done for you lately, John? What has the Earth being a globe done for you specifically lately?
It gave me an amazing salary and a life. I have a house. I have insurance. I have a very stable life.
Salary life, huh?
So what's the problem?
Globe gave you money, a lifestyle that you're comfortable with.
Oh, I'm sorry. Are you not a capitalist too? Are neither of you? Are you guys doing this for free? How much is your app, Dave? $3? Why don't you make it for free if it's
because it costs money to run it? Why don't you pay for it and then I'll make it for free?
John, what's your argument with I've been doing this 10 years, I get $27 a month on Patreon. Do you think that feeds me? Do you think that pays my bills? Do you think that even feeds my dog, John?
So how do you make your money? I mean, everybody has to make money.
Yeah, the creator provides for me, but I've been almost full-time for almost 10 years and I barely scrape by. But you know what? I don't care about living in a cush house if I'm lying to people. At least I'm telling them the truth, and I know I'm telling the truth.
I mean, do you really believe in this? I mean, it just seems like
what's your best globe? Do you have something that prove that? What's your best globe proof? Something physically, like, what's your best globe proof?
I mean, I've seen like I don't deny these. Like space missions, I don't deny NASA.
You don't deny.
I've worked for contracting.
So is this your best globe proof? The picture that was taken from the moon?
No, look, that's not the best one. I mean, there's lots of.
But
the way the time zones. Why you can't see certain stars.
Okay, wait. One thing at a time. Pick one, and then let's address it.
It's accumulation of knowledge. You guys zero and focus on one argument, and that's the thing. There's so many arguments in support of the globe.
Do you believe? So do you believe this picture is real? This is the one they took from the moon. Do you believe this is real?
If that in fact is from,
if that's the one taken from the moon, yes. Okay.
Yes, I have no problem with that.
All right. So where's wait, hold on a second. Why is that doing that? Actually, oh, here it is. Okay. So here's the picture they took from the moon. Now, what is this? This is Africa, right? Here's Madagascar. You with me? Right? This is, I guess that's Antarctica.
Part of it.
And so we have a full Earth. So the sun is behind the moon, right? Full Earth. If the sun was over there or over there, we'd see a Terminator line right here, and then we'd see, this part of the Earth lit, or this part of the Earth.
You're on the day side of Earth. Yes.
So we're on the day side of the Earth. We're on the day side of the Earth. So we know what time this was taken, what day it was taken. And if you look, this is what's lit up on the Earth at that exact time. Here's South America.
That looks like Madagascar and South Africa.
No. Here's Africa, Madagascar, South America, and a little bit of Australia. Where's Australia? Where's South America?
And like
they're
all
in the clouds.
No. Look, come on. Look,
all of Russia and Asia.
This is where the Terminator line is. Look, this is actually wrapped around the side. Okay, where is it? This is out of scale. This is a painting. You've been fooled. They're lying about space, but you believe it. We can show you. We can.
It maps exactly with what the.
No, it doesn't. No, it doesn't. Look again.
It's behind the clouds. I mean,
all South America is in the light. There's no clouds over here. Where's South America? Where's Australia? This is all in the light.
I mean, you're from your angle viewpoint. I don't know.
From,
I mean,
from my angle of
you're just like
viewpoint.
showing me this stuff.
Right. But the thing is, what you have to understand is, this is the other side of Earth. Here's America, right? Here's America. This is Mexico right there, right? And then when we look on a world map and we put it right there, this is what lines up perfectly. You have to believe that all of this land is on the other side of this ball.
And water.
Look, here it is, showing you again, not that many clouds. You have to believe all of that land and water is on the other side of this ball, right here. If you can't say that's fake, and if you say that's fake, all of space is all the stuff NASA tells us is fake. Why would they fake it? This destroys your globe world, destroys it, and I have 100 more of these.
No, I bet you do. I mean, look, if you just project on a flat surface, it's going to be distorted at the poles. I mean,
it doesn't matter. It doesn't matter. Where is the rest of the world? Because when I showed you the other side of the world, all it had was this. It just had this. So then all of this should be on the side that we're seeing here. Remember the other one I just showed you? It just had this on it. It had just this. So all of that is supposed to be showing up over here. You can't be intellectually honest and see this and not understand that you're being. Oh, you know what? I wasn't even showing you what I was just showing you. Hold on. Was I showing you that?
Yeah, it looked good. I saw it.
Okay. Yeah. So yeah, all of that is it's crazy. And then the other argument is, well, look at this picture, the Earthrise. This is the famous Earthrise, right? And I was like, you don't need Photoshop to do that. Look, I did that. Look, I added myself on the moon. Look, I added two Earths. All right. I did that without Photoshop. I did that in Canva, which is a free app. Okay. So just saying pictures from space prove the globe because the Earth is a globe, because why would they lie? Because
I mean, again, that's not why I choose to believe in the Earth anyway. But I mean, you could do like mappings between those images, and I mean, you don't just like
you could, but we've done all of that, and it all is a mess. All of it proves that none of it's real. None of it's real. None of it's real.
I guess I don't really know like where your end goal.
My end goal is to free people from the mind matrix. The globe is a prison for your mind. If you live
how so?
I will tell you. If you live on a globe, there's limited resources. You're a speck in an infinite expanding universe. Asteroids could take us out at any time. We're overpopulated. All of this stuff. And we're not important. We're a random speck that evolved from pond scum. I'm not a random speck that evolved from pond scum. Nathan's not, and neither are you, but we know it. You don't. You think you came from pond scum, right? I don't. That depowers you, right? If you understand that we are,
I mean, if you present it in that light, then sure. I mean, if you have that kind of attitude about it, but I mean, I look at the same sky with the idea of a globe, and I think it's just magnificent. I mean, I think space, it's just a miracle that any of us could actually be here.
So your proof of a globe is what again? Because you brought up the picture.
Well, I told you the stars, the shift of the stars in the sky, the sun.
Wait. Hold on. Wait. One thing. I mean, the stars in the sky. So do you remember? You know the we're traveling. You know how many miles the Earth travels every year? So we're chasing the sun. We're orbiting, right? Forget that. We're chasing the sun at 500,000 miles an hour, close to it. We're traveling 4.4 billion miles a year, never to return to where we were before. Planets, I mean, they say that like 80% of the stars in our galaxy are binary, and some of them are trinary, which means they're orbiting around each other like this, right? Everything's moving, but never once have two stars changed position due to parallax. Never once have you seen two stars cross each other's path due to parallax. Now, we have stars that are close. only 25 trillion miles away, and other ones that are millions and millions and millions of times farther. Everything's moving, but in all of recorded history, no two stars have ever changed position. Or maybe those lights in the sky are close, they're fixed in the sky above us, and they're rotating above us, like Tesla said. Maybe.
Oh, you're talking about...
I'm talking about why, if we live in this crazy heliocentric nightmare, no stars have ever changed positions. You don't have an answer for that.
I mean, everything shifts by the same amount. I don't understand.
Oh, everything shifts by the same amount. So a binary star is...
They're far away.
They're both so far away that all of the millions and billions and billions and billions and billions of miles for billions of years, nothing ever changes because it's so far away. But you ignore the first thing we talked about, the angular size of stars. We couldn't see them, and then you try to point it towards a laser, and not you admit that light attenuates and spreads out and gets weaker, but you still believe that we can see it. You know how many times that the moon...
Because of the power. I mean, and you just chose to ignore that. So I mean, it's like you skip over the thing. You choose to hear what you hear, I guess.
Not true. If the moon's one lumen,
you don't really have any numbers to anything.
If we here's a number for you. If the moon is 1 lumen, I don't know, full moon night, it's 1 lumen. Just for let's say it's 1 lumen. When you get 100 miles from the moon, it should be brighter than the sun for us to see it at 1 lumen at 250,000 miles away. If you use the inverse square law, right, it should be brighter than the sun, magnitudes brighter, for us to see that the brightness that we see it. It would be the same brightness or brighter than how we see the sun. You can't imagine. Polaris, at the distance they say it is, right, would have to be... I can't even think of the number. It's like it's in the sextillions or higher, brighter than the sun for us to see it at the brightness that we see it. But you don't like to calculate that stuff because it destroys your heliocentric world.
Yeah, we had a globe.
We haven't seen every star. I mean, there's stars that we don't see. I mean, that's why the.
Go ahead, Nathan.
We had a Glober on TikTok one time tried to do the math for how much brighter and bigger Polaris would have to be than the sun. And when he got to 32 million times bigger and brighter than the sun, he gave up on the math and didn't want to do the multiplication anymore.
Right.
I'm sure, because he was probably not considering the power output.
32 million times, John.
Because you're just looking at the size. I mean, it's not an aperture problem. It's an output. I mean, nuclear fusion is huge. And I don't think
nuclear
you believe in fusion either.
Here's the good news, Don. The good news is an honest man, when proven to be wrong, must admit he is wrong, or he no longer remains to be an honest man. So there's still an opportunity for you to come out on top and just admit, hey, I was deceived. I was wrong. You're still going to be smart. You're still going to be handsome. You're still going to be charming. You're going to have all that going for you. You're just going to know the truth now. So I think it's a W, but we're kind of going in circles.
Yeah.
I think
I have an idea.
I'm a very honest person, and
I think you're not willing to look at the evidence that we're showing you. I have an idea.
I mean, I think like running an experiment, but I mean, you kind of throw these photos. I mean, it's like you're arguing that NASA is doctoring photos, but then you show me photos of your own experiments. You see how that works?
All right. Do you want to have a little fun with NASA for a moment? We just show you.
Well, we did that last time a little bit.
I showed you. All right, but everything I show you, green screens, wires, bubbles in space, everything I show you, you just make an excuse. And like,
but then like, why do you, I mean, it's like you believe that footage, but then you don't believe the moon footage. Like, it's like you kind of.
I don't believe any footage. I believe it's all fake.
Yeah.
So then you show me footage of your experiments, and then how am I supposed to believe it?
I said, don't believe it. Go do it yourself. I can't go to space, but I can redo the experiments myself. Okay. That's what I did. I got a P900 when it first came out, and I zoomed in on things that should be.
I mean, I'm very interested in doing Earth experiments to show.
If you did one, let's say you found a frozen lake, right? It got and you measured those light. You did the same experiment, and it came out. What would you do? Would you deny it?
I mean, when I run an experiment, let's just back up. When I run an experiment. I mean, you first have to be very careful in your measurements and very precise, and you have to visually verify it. Okay, and then you take your data and you measure and you observe, and then you have to think. You don't instantly, I mean, it's very rare in science when you get data and you just instantaneously know, like, oh, this is exactly what happened. I know it.
Well, and
There's
what we do is,
there's a lot of there.
yeah, we do the experiment, we think, and we look at the data. We have the data. You're assuming data. You're assuming a star is X distance away, made out of gas in a space vacuum, which breaks all laws of physics.
But okay, but then Dave, you have to make some sort of experiment to figure out how far this stuff is.
Okay, well, how about
use some trigonometry? I don't know.
We can see too far. We can see beyond the physical horizon of a 24,901 mile Earth. So
okay, but when I ask you like how, okay, so you don't agree this the distance away from the moon or the sun.
Well, let's stick to Earth.
Then
talk about
figure out an
horizon.
experiment that you can run to actually measure a distance.
Okay, let's look
just
at
speculating.
No, let's measure distances. We have on the app, if you go to the there's an experiments page, go to Taboo Conspiracies channel. He's got all experiments that have all been done and laid out for you, shown, and they show they lay it out so you can't deny it. They show you all of the evidence and the setup and everything, so you don't have to do it yourself, but you can go do it yourself. That's the thing. We can see too far. Therefore, the Earth is 1,000 times bigger than they're telling us, or it's flat. We can see observations that show that would require the Earth to have a radius of over 100,000 miles, and the assumed radius is 39,850. What is it, Nathan?
3,959 miles.
3,959. All right, so we can see things that would require the Earth to have a radius over 100,000 miles. That's a problem.
240,000.
240,000 miles, right?
And I had a Glober on TikTok extend the radius value using the refraction slide bar to 39 million miles. So we're making observations, and Globers are just making the radius value of the Earth 39 million miles to compensate for us seeing way too far. This is not science. This is not being honest, bro.
I guess like I would like to see those kind of
well, you can. It's there. It takes time and effort, and that's a hard thing for you to do, because if you take the time and effort, let me finish what I'm saying. If you take the time and effort and actually look at this stuff, it's going to blow up your world. So I don't think you really want to do that.
There are some problems discovered with these experiments, would you be so honest to admit that there's a problem in your model?
Sure. We don't have a solid model. We just know that your model doesn't work.
Well, perhaps you guys should work on that.
Well, we are working on it.
Yeah, that's for sure.
Measuring the physical Earth, you guys like to.
I think
I could like to finish a sentence.
Okay.
You guys like to look at people in the past that you've never met, that you don't know even if they're real, and you like to look at the lights in the sky, and that's where all of your stuff comes from. You don't like to look at the Earth because the Earth measures flat.
Maybe it's just it's so
big.
It's not a reliable optical source for
measuring the Earth is not. No, we can.
How to measure? I mean,
we do mirror flashes. How about a mirror flash? Let me ask you a question. You know what a mirror flash is? I got the sun over there, and I could flash the mirror, and I could, you could see the flash, right? So what if you were on the other side of my house, and the sun is above my house? Could I flash you with the mirror?
No.
Of course not, right? But we have mirror flashes where there should be a bulge of water 600 feet high, but they can see the mirror flash.
I'm sorry, I don't.
So we have over a body of water at 10 miles, there should be 66 feet of curvature, right? We've done them farther than this, but we'll just go 10 miles. And we can have somebody with a mirror on the sand flashing the sun, and the person can see that mirror flash from the beach. Now, if I put my house in the middle of the lake there, they shouldn't be able to see it. forget my house. My house isn't 66 feet high, right? But we've done them even farther. What's the farthest mirror flash? You know, Nathan?
Personally, I've done 17 miles across the Salton Sea. There should have been 170 feet of curve in the middle.
170 feet of curve, but people can see the flash. 170 feet.
And they just did a laser observation 23 miles apart. I just uploaded the video. It's like, man, we see way too far. It's not like slightly too far. We're talking the radius of the Earth would have to be 10 times bigger than they're telling us. If that's the case, well, then the Earth's speed around the equator would be 60,000 miles an hour. We don't feel it. I mean, it just gets more ridiculous.
Right. And the other thing is, people say, you know, the global argument for lasers is, well, you're not seeing the source of the laser. You're seeing the laser come up over the curve, and you're seeing the point of light there. Cool story, not real. But then we said, okay, let's do it with a mirror flash, because a mirror flash is a line of sight. There's only way to see a mirror flash is line of sight. You have to be able to see that mirror, and that brightness penetrates far enough the person can see it, and the Globers don't even want to argue it. Don't even argue it. We have from mountaintops to other mountaintops, hundreds and hundreds of miles we can see.
I'll tell you what. I'll look into that experiment. I'll look into it. I think this is an interesting topic.
So go to Taboo Conspiracy. He's got a bunch of them. All the work's been done for you there. Go there and say, hey, I like that one. I'm going to go verify that one. Right? He's just done all the work for you. Just trying to do it all yourself, it's going to take forever. You'll never do it. He's done the work for you. He's highlighted. He's documented it. He's a lawyer. He does it really well, and he documents all the points. So there's really no arguing. John, I think go ahead, Nathan. We're going to wrap it up.
What part of the country? Because I've done observations in 12 states. I'm just curious where you're at, brother.
California.
Oh, I grew up in California. I started testing the Pacific. That was the first place I went.
Okay.
And so Salton Sea is another place.
I haven't actually been there. I'm originally from Kentucky, actually, and then I moved out here for a job, and then, but you know, the Salton Sea is definitely on my list of something to check out, because
I lived in Lexington and Louisville, Kentucky. I used to sell MetroNet fiber optic internet out there.
No way. No, that's where I went to school at UK. That's
I
crazy.
used to go and share Flat Earth on the campus, dude, and trigger all the students.
Yeah. All right.
Maybe we were on there at the same time. Who knows?
Maybe. Hey, John, you're a real sport, and you're awesome for coming on with both of us. And it gets a little heated, gets a little emotional.
I apologize for losing my temper. Okay,
that's okay. That's okay. Listen, I get it.
We all have thick skin, so like, let's just
yeah, no problem. Listen, I like you. You're a good guy. If you want to get if your buddy wants to do this again, I would say come with a list of Gold Globe proofs. And then we'll do it again, and we'll have another discussion, and we'll just go through them, and you can take it or leave it.
Okay. I mean, he actually really wanted to do this. He had a migraine come up, and
it's all right. If I was spinning on a ball too, I'd have a migraine also.
Hey, Dr. John, if he could get the list compiled together, so I could come with like the best sources and the best evidence to combat that next time we meet, please. I'd love the list.
If you want to do the list ahead of time, that's good also.
Okay.
Whatever you want.
Okay.
All right.
We can organize a thing. Yeah. I really think these conversations are good. I mean, I think healthy skepticism is good for both parties. So I hope we can all agree on that.
Go ahead, John. Go ahead.
When you become a flat earther, John, no one's going to take your birthday away. No one's going to eat you. Everything's going to be okay. If you fall off the globe, then I will catch you time after time, John. Don't worry.
And don't be too afraid to turn back course on your side either. Okay?
Yeah. So, unfortunately, nobody's ever gone back from flat earthers. We have the ability to change our mind. We do, because we did. Okay.
Sure.
We've proven that we can take our world belief and switch. So we're willing to go back. But, again, physically measuring the Earth is the way to prove it. Looking at the lights in the sky, that just tells us what we know about the sky. All right, John. Thanks.
All right.
Good to see you. Well, thanks, man.
Thank you, guys.
Bye-bye.
You were awesome. Right? Pleasure meeting you.
Yeah, you too. You too. We'll talk again.
All right. Bye-bye.
All right. Bye-bye. Bye.
Nathan.
Yeah, buddy.
Good. He's a good guy, but man, it's tough.
I asked him what the globe did for him. He says, it gave me a lifestyle and I'm comfortable. And there it is for you, bro. That's it right there.
Yeah.
So
Yeah, it's amazing. And when I mentioned solar panels, that's the truth about solar panels. I was like, how do solar panels work? And I did a lot of research into it. And I was talking to the best engineers in the solar business, and they're like, yeah, it's just a theory. They think it works like this, and they can't see it because they never considered what the sun is.
Yeah, you can't make solar power from a fire, so they can't reproduce on their model
Yeah,
conceptually what's actually going on to make that happen. So,
yeah,
but yeah, really upset that you were like, no, I know
yeah.
what
It's
they.
like I could build a solar panel. I can build things too, but your theory on how it works doesn't have to be right for it to work. It
Yeah,
works,
exactly.
but he doesn't understand. It's right. It's so simple. For someone that understands that we're not in a heliocentric world.
Yeah, it's like you can boil water, but then you claim there's a dragon underneath the stove blowing fire up at the pot. It's like, okay, well, you still get boiling water, but that doesn't mean there's a dragon in your stove, bro. You know what I mean?
I've never considered
So.
that.
That was fun. Thanks for having me up, Dave. I appreciate it.
All right, Nathan. That was fun. We'll do it again, and I appreciate it. Appreciate it, man.
I hope
Thanks.
so, bro. Yeah, we'll talk soon.
All right, see ya. Bye bye.
Later, buddy.